There you go. Hi, everyone. Welcome back. This is the final session of talks. We have 2 times 2 talks, and we'll start off with 2 talks on subduction. And maybe, Daniel, you want to start sharing your screen? You can give that a try.
Sure.
That's your email.
Yeah, I'm trying to. There we go.
Yeah.
Nothing happening there.
Okay.
Can you see my mouse and my screen okay?
Yes. I see your mouse and the slide is full screen. All right. I see a lot of people joined. So as I said, welcome back. We'll start with 2 talks on subduction. Daniel, the floor is yours.
Cool. Yeah, so I'm Daniel. I'm a PhD student at New Mexico Tech working with John Naliboff. And I'm going to be presenting some of my PhD work titled 3D Subduction Modeling Using Aspect and the Geodynamic WorldBuilder with an application at the Hikurangi margin. So the goals of my thesis are to develop this 3D regional aspect model of the Hikurangi Kermadec subduction system, and then collate some regional geophysical data sets and use that as constraints on the models. These 2 first points are what I'm actually going to be presenting today, but the ultimate sort of arc of my PhD, hopefully, is to take the solid models I'm about to show you and use them as a basis for implementing 2-phase reactive fluid transport, and then see how that fluid transport impacts the output of the models and the fit to the data set. So a little bit of motivation is that there's been a lot of really great studies over the last few decades providing a significant amount of insight into volatile transport at subduction zones and the impact of volatiles at subduction zones, but there's still significant questions remaining regarding how all these things work in 3-dimensional numerical models. I'm showing some figures from various studies on the bottom here. The left is using EM to estimate input of volatiles into a subduction zone. This middle one is a 2D subduction study with volatile pathways being shown. And then this one on the right was a seismic investigation into volatile transport. And I'm going to be focusing in on the Hikurangi subduction system simply because there's an abundance of geophysical data there that constrains volatile influence at different parts of the subduction zone. So I'm showing this figure here on the left, which is a map view of the North Island of New Zealand, looking at the Topo volcanic zone, which is an area of some of the most voluminous arc volcanism on the planet. And arc volcanism has a lot of ties to volatile input in the system. This middle figure is showing a 3D attenuation tomography image where they image high attenuation in the mantle wedge here, which is again likely attributed to devolatilization of the slab. And then this image on the right is showing the slip deficit for a slow slip event that was observed on the interface of this margin as well. And there's this idea that pore fluid pressures along the interface impact slip behavior, and that is why there was a slow slip event in the Hikurangi system. That's at least one of the ideas. And so I'm going to reiterate again that this is everything I'm going to show you is the combination of the solid subduction for this part of my thesis. Sort of this first phase is what I'll be showing you, the thermomechanical model of the Hikurangi system. But the ultimate goal is to create this integrated Earth model through this NSF initiative to couple my subduction models with the models that I believe Arushi outlined yesterday in her presentation as boundary conditions on my regional subduction models, and then implement the reactive 2-phase fluid transport and see how that varies the results. And I'm going to be going to the University of Florida in, I guess, just under 2 weeks now to work with Juliana, Renee, and Menno and others on getting this reactive fluid transport into my subduction models. So super exciting stuff. But with that being said, let's start building up this regional model. There's a bunch of tectonic features in the Hikurangi area that may be important and affect subduction processes. And I'm going to incorporate all these into my model using the WorldBuilder. So not shown here on this map view is the slab, but obviously the slab is very important in driving the behavior here. We're taking the data from the slab 2.0 database, using that to initialize the slab. And then we have this Hikurangi plateau, which is a large igneous province that also you can't see in map view, but it is actively being subducted, which we include that as well. We have back arc spreading on the overriding plate. The top rift zone on the North Island of New Zealand is around here. We have this batholith in red, and then flanked on either side of that are these terrains. And this is our representation of these tectonic regions in map view in aspect. This is again collated using the WorldBuilder. And these different provinces are approximated through seismic imaging by our collaborator in New Zealand. And we're implementing these as different lithospheric thicknesses currently. There's no other material difference, although they are compositional fields. So if we wanted to investigate different material properties, we could do that. Currently, just strictly lithospheric thickness variation. The temperature in our slab, which is here, this is a 3D image of the slab, follows a plate cooling or half-space cooling model with an approximation that accounts for transit time in the convecting mantle. And this is in the WorldBuilder, and this is a reference to Magali Billen's AGU poster where she presented this. And then we take that WorldBuilder initial condition and we put that into aspect, and we calculate an instantaneous solution to the Stokes and advection equations. We do this in a spherical chunk geometry with an adaptively refined mesh that goes from 40 by 40 by 40 to 5 by 5 by 5. And we adaptively refine the mesh, as you can see here, within the slab, because that's the area that we care about. We use a nonlinear viscoplastic rheology that includes wet and dry olivine creep, Pearl's creep, Drucker-Prager plasticity, and then within the slab and, well, everywhere, we include phase transitions for olivine and eclogite to get more accurate estimations of the slab pull force. I want to emphasize that we're not kinematically imposing any velocities here. Every velocity result that I'm going to show you going forward is a dynamic solution with no velocities being imposed anywhere in the model. So we take that model setup and we test 3 different model parameters, which are the plate boundary rheology, the subducting plate thermal structure, and the upper mantle rheology. And we see what effect these have on our 3 different observables, which are the subducting plate velocity, the anisotropy, and the downgoing plate dehydration. I've run a suite of models, but I'm only going to show you the results for one particular model, which happens to be one of our better fitting models. And this model has a 20-kilometer wide interface along the subducting overriding plate with a minimum viscosity of 10 to the 19 in that region. We use a plate cooling model for the subducting plate, and we use wet olivine for the rheology of the upper mantle. I also want to do a quick shout out that this type of WorldBuilder data collation with instantaneous 3D subduction models, they're being done in other regions. And the one that came to mind, I'm sure there's others, was Menno Frater's Cascadia subduction model. And here's an image from there. I'm sure he'd be happy to talk about his also. And if anyone else is doing a similar thing, I would love to hear about it. But this was the only one that came to mind. So let's start looking at some results. These are surface velocities on the left and 3D velocity patterns on the right. Starting with the figure on the left, the map view here is showing the trench and the North Island of New Zealand here. And the black lines correspond to the more well-calculated convergence rates of the Pacific plate with the Australian plate. And the red arrows are showing the velocities at the surface from our aspect models at the same point. And again, these are dynamic velocities. These are not imposed, but we are getting a very strong fit to the convergence rate, not only in like direction, but also in magnitude across this several degree span of the trench. And then in the 3D velocity field, we can see that we're getting, classic sort of wedge convection style patterns where it comes in and then drops down with the slab. Going to the regional anisotropy, we're using a DREX implementation that is in aspect, and this is the citation if you're interested in that implementation, but we're calculating CPO on particles, and we compare our results to regional anisotropy measurements beneath the North Island of New Zealand from this paper by Eberhard Phillips in 2013. This is an image just showing what the anisotropy that she found was in the region, and this is what we're using to constrain our model. So we're looking here at 2 different cross sections of depth. This one is at 85 kilometers. This one's at 155 kilometers. And the gray area represents where the slab within my model is located. Excuse me. And Once again, the black lines represent the data set, and the red lines represent our aspect model output. And what we see in this cross-section of 85-kilometer depth is within the sort of interior of the slab, we're getting a pretty strong fit to the anisotropy measurements. And as we transition, this is the mantle wedge over here, from the slab into the mantle wedge, we actually kind of start to see an anti-correlation where we're almost exactly orthogonal to the fit or to the data in a lot of places. And the same is true at this deeper depth where we get pretty good fit here and actually back here as well on the not mantle wedge side, the basal side of the slab, but we deteriorate into an anti-90-degree fit towards the mantle wedge. And I haven't tested this yet, but a hypothesis that I have is that this CPO calculation that we're doing is only accounting for the A-type olivine fabric. And there's this idea that if you have significant hydration of olivine, the fabric will transition from an A-type to a B-type fabric. And the B-type fast axis actually orients orthogonally to the A-type fabric. And if there's anywhere within the model where we would expect there to be significant hydration, it would be in the shallowest most part of the slab in the mantle wedge, directly above the slab. So I think this is definitely, I need to investigate this still, but this is at least an idea that I think makes sense for why this might be sort of deteriorating the way it is deteriorating. Yeah. And then the last thing we're going to talk about is the dehydration patterns. We're using a parametrization of phase diagrams for 4 different lithologies to estimate devolatilization of water. And these lithologies are sediment, mid-ocean ridge, gabbro, and peridotite. And we're using phase diagrams from this paper by Tian et al. 2019. And I'm showing an example of what those parametrized diagrams look like. This is the actual perplex output for a mid-ocean ridge basalt. And this is the parametrized phase diagram that they came up with for mid-ocean ridge basalt. So we're using this one. And we're using this because when we get to the stage where we're doing this 3D coupling of 2-phase flow, it's going to be very computationally expensive probably to use a perplex lookup table, whereas a oh my God, that word just gets me every time. You know what I'm trying to say, is going to be a lot faster than using a lookup table. And so this is the result that we get using this lookup table. The top panel is showing the surface flux of water, and the bottom is showing the weight % water distribution through a cross-section of my slab with depth. And what we're seeing is, initial sort of sediment dehydration, shallow depths, and then we get a big spike in devolatilization in this part of the slab. And these black vertical dashed lines represent the lateral extent of the topovolcanic zone. And so we're seeing this large flux beneath the area where we're seeing the most volcanism at the surface. And so the idea is that this would lend itself to melting the mantle and generating that large volcanism that we observe at the surface. And so once again, outlining that, this is the last couple of slides. This is the culmination of the solid part of this thesis that I'm working on. And I talked a lot about fluids, but there was no fluid interaction within the aspect model. That is something that we're working towards. And hopefully maybe by the next user meeting, I can talk about that because it will be done. So I'll leave my conclusions here. Just saying, once again, we get an excellent fit to plate velocities on the surface, a strong fit to anisotropy within the interior of the slab with a hopefully a reason for why we're not seeing a strong fit in the mantle wedge of the system. And then we're getting a good agreement with where devolatilization should occur based on surface volcanism. And I will stop there. I guess I just stopped sharing my screen, and then we move on.
Yes, thank you, Daniel. That was great.
Cool. Yeah.
And we're right on time. So we'll wait with the questions till after the next talk. And the next talk is by Antoinette. So if you want to start sharing your screen, and then you can get started right away.
Perfect, thank you, Anne. Right, can you see my screen?
Yes, and I see your mouse moving as well.
Perfect. Great. So thank you to Daniel for that excellent introduction to the complexities that make subduction zones and subduction processes. Now let's take a bit of a step back and think about subduction on a global scale instead of a regional scale. And as we've seen from that, from the previous presentation, but as we also all know, subduction is a very complex and very heterogeneous process, right? And one way we can see this heterogeneity is by looking at the slab morphologies through seismic tomography models or seismicity. And for instance, we have slabs like the Japan slab, where we have slab deflection and flattening at 660 kilometers depth. But we also have slabs which sink steeply and directly into the lower mantle, like for instance, the Tonga slab. And this diversity in slab behavior and slab morphologies is not something that only occurs across different subduction zones, but sometimes we can also find it at the same trench. And a great example of this is the South American trench, where we have flat slab segments here at Peru and Chile, which are right next to steeper dipping slab segments along the same trench at the same subduction zone. And this heterogeneity and this diversity is not something that only occurs in space, but can also occur in time. And this is beautifully exemplified by the northwestern margin of the continental US, where we have this deformation within the Colorado Plateau and the Basin and Range, which is left over from the flat slab episode during the Laramide orogeny approximately 60 million years ago or so. So looking at all of this heterogeneity, the question then becomes, what is the main driver, what is the main control that determines the style of subduction and the slab morphology at the trench and the deeper depths, and does this in any way affect the topography on the overriding plate? And previous work has assumed that this control or this influence is due to the heterogeneity of the subducting oceanic lithosphere as this gets to the trench. However, recent work by Adam Holt and co-authors from 2005 suggests that actually the overriding plate thickness can directly influence the angle of the slab at the trench, form models with plastic yielding. And work by O'Driscoll and co-authors from 2012 and 2009 suggests that the presence of a continental keel will encourage a slab to deflect and flatten underneath the overriding plate. So clearly the overriding plate is important. However, when we look at the continental overriding plate, we can see that this is extremely heterogeneous, and we can see this heterogeneity in this S-wave velocity map by Pearson and co-authors from 2021, where if we say, for instance, look at North America, we can see that as we move from the margin towards the continental interior, we see this increase in S-wave velocities, indicating that now we are in a region where the lithosphere is colder, stronger, and possibly older. The other thing that we can notice from looking at this map is that these continental cratons, or these older parts of the continents, are very diverse in terms of their size and their shape, right? So then the next question that we asked ourselves was, is this important for the slab dynamics? Does this have any influence, or does this in any way affect the evolution of deformation on the overriding plate? And to answer this question, we use aspect to solve for the contribution of mass, momentum, and energy, and model subduction in a 2D Cartesian box. And in our models, we include a parallel rheology and also plastic yielding. And we use adaptive mesh refinement to approximately get a resolution of around 500 meters at the surface within the continental overriding plate and outlining the slab. We also have a free surface, and we start off with a slab that's 200 kilometers long and steeply dipping at 70 degrees. And we include heterogeneity in our models by implementing a continental keel some distance away from the edge of the continent. And so these are some of our results, and what I'm showing you here in browns and greens is the topography, and on the bottom left of each topography screenshot or plot, you have the slab morphology. And on the top left, we have a model with a homogeneous overriding plate, and on the right and bottom we have a heterogeneous continental overriding plate. And just eyeballing the slide, we can see that the slab morphology is actually not that very different. However, the topography is, particularly if we compare our homogeneous case here with our heterogeneous cases. And we can see that for our heterogeneous cases, we have a well-defined zone of deformation within the continental margin, which is missing for our homogeneous case. The other thing that we can notice is that this zone of deformation varies both in terms of the topography and the amount of basins and the subsidence based on the type of heterogeneity that we implement in the continental overriding plane. And if we look at the trench retreat and compare that across 4 models, we can see that the trench retreat, particularly for a homogeneous case and our heterogeneous cases, shown here in blue, magenta, red, and black, varies quite a lot between the different implementations. So what I'm showing you here is the amount of trench retreat on the y-axis and the extent of the deformation region on the continental overriding plate on the x-axis. And the different colored circles represent different models with different continental heterogeneity. And the first thing that we can see is that there is a distinction between models where the heterogeneity is geometric in nature and models where we change the rheology of the heterogeneity that we implement. The other thing that we can notice is that we can broadly classify the behavior of these models into 3 groups. The first group is those models where we have limited trench retreat and also a limited amount of deformation on the overriding plate, where we don't really see the basin and the subsidence and extension. The second group of models is models where we have a considerable amount of trench retreat and this well-defined region of subsidence bounded by 2 higher zones of elevation, so very much a horse and graben kind of morphology. And the final group is models where we have an extensive amount of trench retreat and a very wide and extended deformation region on the overriding plate with multiple basins and a considerable subsidence. Okay, so far we've been talking about the continental interior, but what about the continental margin? Do variations matter for this zone in our model? And the answer is yes, very much so. So over here, I haven't changed the continental interior, but I have changed the properties of the continental margin. And on the top left, we have a narrow margin. Top right, we have a thin margin. Bottom left, we have a very strong margin, and bottom right, we have a weak margin. And we can see that, first of all, the slab morphology is different now, but the topography is also very different. And if we have to look at the trench retreat for each model and compare this, we can see that the trench retreat varies considerably across all 4 models. And once again, plotting the amount of trench retreat against the extent of the deformation region, we should see, seems like my, okay, we should see that there is again a distinction between margins where the variation is mostly geometric or rheological. And if we look at our models with rheology variations, we can see that we've got this really nice relationship where as the amount of trench retreat increases, so does the extent of this deformation front or this deformation margin. But this relationship does not seem to be the case for our models with different margin geometries. So to understand this behavior in a little bit more depth, what I'm showing you here is the topography at the top, the velocities in the middle shown in blue, where darker blues indicate higher velocities, and at the bottom the strain rates, where more purple the color, the higher is the strain rates. And this case is for our standard continental keel model. And we can see that what's happening here, if we look at the velocities, you can see that as the slab sinks through the upper mantle, it induces this viscous return flow in the mantle wedge. And essentially, the presence of the continental keel is funneling and focusing this return flow directly underneath the continental margin. And this return flow is then dragging the continental overriding plate towards the trench. However, it's not doing so uniformly. Instead, we can see that actually we have the continental overriding plate that's moving at different velocities. So at the very edge, we have the fastest velocities. In the middle, we have the second sort of batch of velocities, and then the continental interior is moving very, very slowly. And we can see that in the middle within the continental margin, we've got this partitioning of the velocities, and that corresponds to this focusing of the strain rates, which then brings us back to the surface where we see this subsidence in this basin forming between these two sort of horst morphologies. And this trend is even more pronounced when we have a weaker margin. And in this case, we see that we not only have one partitioning, velocity partitioning within the continental margin, but actually we have 4. And if we look at the strain rate localization within the margin is actually higher in this case. And we see that the deformation front within the continental margin is wider, and it has considerable more subsidence. And we also see multiple basins forming. But when the continental heterogeneity is very small or very thin or not present at all, we see that when the induced viscous flow in the mantle wedge is much smaller and it's not as focused and as funneled within underneath the continental overriding plate, we can actually see there's a bit of a gap between this return flow and the margin. And we can see that in this case, we do not have any partitioning of the velocity within the continental overriding plate, and the continent is moving as a coherent whole towards the trench. And this means that we do not have this strain rate localization within the continental margin, and therefore we do not have this extension and this subsidence in our topography, which we see in the previous 2 cases. Okay, so we've talked about the continental interior, we've talked about the margin, but what about the subduction interface? Does this matter? And the answer is yes, very much so. So what I'm showing you here is the same model setup as before. We haven't changed the keel or the continent or the slab, but I've changed the strength of the interface. And the first thing that obviously catches your eye is the fact that we have a flat slab that's forming self-consistently within our model. And the second thing is that the topography also looks very different compared to the previous cases. We still have this sort of localized deformation within the continental margin, but it's much deeper. And it gets even deeper once we get this flat slab forming. So at this point, we have the flat slab formation. We see that we've got increased subsidence within the continental margin, but we also see a secondary subsidence within the continental interior. And this is very reminiscent to what we see today in South America, where we have flat segments in Peru and Chile. The other thing that is interesting is that we've got this really high trench retreat at the surface, and this corresponds to the fast slab rollback that we get in the upper mantle. Okay, so what I'd like to draw your attention to, first of all, is this figure here on the left, which is a plot of the pressure, where pink colors indicate negative pressures and green colors indicate positive pressure. And what you can see is that at this stage, when we are forming the flat slab, we have a considerable amount of negative pressure in the mantle wedge. And this is actually what's helping to drag and essentially suck the slab upwards underneath the continental overriding plate. But if we look at the morphology of the slab, there's another thing I'd like to point out, that when we think of flat slabs, we generally tend to think of them as something that directly underlies the continental overriding plates and shuts the continent off or away from the mantle wedge. But actually, we see that this is not the case. We still have these zones of dilation here and here, and this is where we've got mantle material that's coming in and then flowing out as the slab rolls back. And this is important because in these zones, we might be getting mantle material that might be getting hydrated from the slab devolatilization. And this might have obviously important consequences for volcanism, but also for critical melt for critical mineral formation. And this is something that I've just started working on with Ben Mather from the University of Sydney, where we're trying to figure out how much devolatilization you get from the slab. And once you get that, where does that melt go? And this is something that I'm hoping to talk maybe to John and to Daniel and to Julian about trying to implement melt yeah, where does the melt go in subduction zones? So I need to conclude really quickly before we run out of time. So the continental heterogeneity matters, not only that it exists, but the type of heterogeneity and where it exists matters, both in terms of the slab dynamics, but also for the continental deformation. And this is because the heterogeneity essentially controls where and how the plate velocities are being partitioned, which is then reflected in the slab behavior and in the surface topography. And this might explain why we see, for instance, some regions with extended and really big back arc regions and other regions where the back arc is very narrow and not as extended, and why perhaps we can get these intramontane basins in places like Peru and the Basinin Range. And that's it. I hope I'm still on time.
You're good.
Perfect.
Thank you. Yeah, those were two great talks. Let's open up the floor for questions. So if you want to just raise your hand if you have a question, then I can see. There you go, Daniel.
Yeah, super interesting. Really good talk. I was just curious, and sorry if I missed it, but you talked about places on Earth where you do see like flat slab subduction, like in Peru and everything. But did you mention how the models that you got with flat slab subduction, like how the overriding plate structure is like similar to those margins? You know, have you investigated that?
So do you mean how the topography matches with the, like how the topography from my models matches with the, right? So
Yeah.
one thing that we are struggling to get is the high elevation that you would see for the Altopiano, for example, right, in flat slab regions. And you can get that if you force the convergence. But if you let the flat slab develop self-consistently, then I get a lot of extension towards the, like, I think after like 5 to 10 million years. So for the first 10 million years, I do get the Altopiano topography, but then I get extension after 10 million years. And the reason is because you've got a lot of this partitioning within, a lot of the partitioning of the velocities within the continental margin, but also because the overriding plate is slightly tilting towards the trench. And so that kind of helps decrease the elevation, right? Yes, so that is, so the high elevation on the continental margin does not match with what you see in topography, but you do get like an elevation and then a subsidence and then an elevation again, but we don't get the same order of magnitude in terms of topography. But we do what is interesting, which is, as far as I'm aware, something that I don't think other people have managed to get dynamically, is the second zone of subsidence within the continental interior, which is something that people struggle to explain, why they have got this subsidence on a flat slab, on the back end of a flat slab, and we do get to see that. So I guess the answer to your question is sometimes yes, sometimes no.
Awesome. Cool. Thanks.
All right, Aggie, you're next.
Okay. Thanks for both of the talks. They were very nice. I have a question for both. First, maybe to Daniel. I'm very curious, how do you have like model the LPO in instantaneous models? Because like what kind of like time frame do you have to create textures? Because with some experience that we had with Ejun of like subduction, like textures around subduction zones, they usually get up to like quite small strains, even through like a couple of millions or tens of million years of evolution. So in, I don't know, in an instantaneous model, how much strain do you get?
Yeah, so yeah, I guess I didn't really go over that, but we're assuming that the particles where we're calculating the LPO are fixed in space. So that's definitely an assumption. And that means that what we're doing, calculating the LPO, is like invalid in a lot of the places. And that's the reason why I chose the depths that I chose, because we accumulate it, we just take the solution and we run it forward for 10 million years to just see how the LPO develops. But I chose significant depths because I would imagine that if you have LPO coming in underneath the overriding plate and then hitting that mantle wedge, there would be a lot of dynamic change that we wouldn't be capturing by keeping the particles fixed. So my idea was, if I go 85 kilometers depth, hopefully by that point, 85 kilometers of just like going along the slab, it won't really matter the history that you get from entering the mantle wedge. But that's definitely an assumption that we're making and have to justify. Yeah.
No, that's good to know. I will not ask my other question that we discussed at HU. About the
this is something that I'm thinking about it. Yeah.
And can I ask also from Antoinette quickly? In one of the last slides that you were showing, was showing that like the part of the slab that becomes like flat slab, then it can like dehydrate. Can it like dehydrate? Can the slab actually dehydrate twice? Because I assume that even also in the first time when it goes into subduction, it would dehydrate. So is there like some kind of limit of like how much can it dehydrate in one place or the other? I mean, so, probably you didn't model it yet, but
so that is a great question. That's one of the things we're hoping to answer, right? So what is interesting is that the slab doesn't, so the second bit, right? So this is the slab, right? And this is the bit that's close to the trench, and this is the edge bit. So that isn't always flat. So it sinks steeper and then it's kind of pulled up upwards. So what is really one of the main things that we're trying to figure out is, when does the devolatilization happen? Does it devolatilize when it sinks, or is it because maybe it's sinking so quickly it doesn't devolatilize enough, and then like there's still some water left and it devolatilizes once it's kind of sucked upwards and flattened? So those are all really, what I think, interesting questions.
Yeah, okay. That's what I would think as well. That if it goes fast, then probably it doesn't lose all the water.
Yeah. And it's sinking really quickly as well. So that is what we're trying to figure out.
Okay, Menno?
Right, well, great talks, both of you. I have a question for Daniel. If I understood correctly, you're just using the CPO with A-type fabric. I'm wondering why that is, and why you didn't use, because there is an option in there which you can use all types of fabrics, which it can automatically select. So I was wondering why you specifically went for the A-type fabric.
It was mainly because it was easier as like a first run through, because the way that we were sort of ideally thinking about doing the different fabrics was imposing a water content, because from my understanding, since I haven't done it, you have to create a compositional field called water that the CPO algorithm like samples to see what the water content is and then changes the fabric accordingly. So I would want ideally to have the water composition within the slab and mantle wedge in that area where we expect there to be water. And that was just something that I was like, I don't necessarily want to do that. I just want to see if this even works, gives us anything cool, and then use that as a motivation. So that is definitely something that I want to do. And I can see how I can just use the WorldBuilder, I guess, to create that composition parallel to the slab surface. That would be
it would be interesting to see if the direction would change if you would allow also other fabrics. But very cool. Thanks.
Yep. Yeah, of course.
John, you're up.
Yeah. First, thanks, Antoinette, and for the great talk, of course, Daniel. I just wanted to follow up on your point about the CPO. And so this is, if you have, or anyone else has any ideas on how to address this, we're basically out of ideas. But typically, like if you look at like the 3D models Peter Van Keck and other people have done, where you oppose the subducting plate, is you oppose the velocity along the subducting plate, then it's fine to do a time-dependent calculation with the CPO because things aren't moving. But in our models, like you have slab, the slab, there's trench retreat, things are dynamically evolving. And so then basically, unless we fix things in place, then you're mixing in all these other signals where the particles might be moving, but then the compositional fields would be stuck in place. And so you're basically getting this mismatch between two things. So this was basically the only option we could think of that could work, where basically the solution for the CPO is not valid in areas where a particle may have just gone through a transition region in like the velocity and strain field. I mean, the other option would just be to let the model run for 20 or 30 million years, but that's really expensive. And then maybe the dynamics of what you're actually trying to model for an instantaneous region of change. So if you or anyone else have any other ideas on how to address this, we would love suggestions, because we have not been able to come up with anything else.
I think this is like a valid test. What I pointed out to Daniel is that nothing starts from random when it gets to subduction zone. And actually within the slab, I would say that because inside the slab, you don't have a lot of deformation, and it's also very cold, so you don't really overwrite. That's something that would be interesting to check. How much time do you need to overwrite frozen in textures? But then I would actually expect those textures to like dip mostly downwards, I guess. But yeah, this is something that may be also worth considering. But again, we have to have Ijun implementing initial textures into the WorldBuilder first for that.
Yeah, it's going to be super interesting to see that. And one important caveat is that the data that I'm using to constrain the CPO is actually only, it doesn't have vertical components. So the anisotropy I see in the slab is purely like azimuthal. There's no depth. They don't calculate that. So I wouldn't even be able to compare that. So that is kind of the limit. Yeah.
I think, that was in the Tonga subduction zone, but I have seen vertical components as well. Not on that.
Thank you. It would also be, I also wonder, one thing about your work is how much anisotropy plays a role in of course in these areas too, but that's very much
good question.
That's later work many years down the line. I had one quick question. I had, realizing the time, I had one quick question for Antoinette, and that I'm wondering, in terms of the results for the flat slab, I'm wondering, does the timing of when sort of the flat slabs develops and the topography on the overriding plate, is that maybe consistent with like what like the laramide originated in the US? So like have you guys compared maybe like the timing of events to something like the laramide?
So do you mean like when what's the delay between the flat slab formation and the topography response?
Exactly. Yeah.
No, haven't really looked at that, but that is a very good point. So what is interesting is that the moment that the slab starts to flatten, so even before it's like flattening the overriding plate, the moment that the slab starts to essentially be sagged upwards, we see that there is this increase in subsidence. So the surfaces really feels that really quickly, and I guess that's because you've got this negative pressure within the mantle wedge. So I guess at a certain point you need to figure out, right, when does this topographic signal come? I mean, at which depth do you get the surface response from the? I phrased that wrongly, but what I mean is, at which point does the surface start to feel like? At which point is your topography the result of like the flat slab, and when do you consider the flat slab starting to form? Is it when it's starting to go up, and how do you read that from the geological data, right? And how do you kind of tease that out from the final topography that you get once you've had the final flat slab? So that's something that we thought about, but haven't really kind of found a way to untangle that yet. But yeah, if people have any idea of how to like maybe answer that question or untangle that topographic signal, I'm all ears.
I see that 2 more people have their hands raised, but we're already at the limit for the questions. So either you type your questions in the chat in the interest of time, or ask them maybe after the second round of talks. Is that okay with you both? Okay, good.
Yep, I think that works for me.
Thanks. Then thank you again to the speakers and all the wonderful questions. And we're going to move on with a talk by John and then one by Mo. So John, if you want to start sharing your screen.
Can you see the same?
Yes, but you're not full screen.
Great. Am I there now?
Now, yes.
Great.
Wonderful.
Thank you. So first, so what this talk is summarizing is not really work that's been done. It's work that's been proposed. So it's basically a conceptual idea, which we currently have review to work on at NSF. And so the idea is creating a common repository for geodynamic supporting software. And we've initially termed our repository for this type of software GDMATE 8. But that is open for discussion. I'll get into details of what all this is. First, I want to acknowledge that this is a large effort, something we've been talking about at CIG for many years, and we've just started working on in the last 2 years. And the current people involved, at least in putting together the proposal, includes Lorraine, Mo, and Maglaville at UC Davis, Dylan Dassey at Tufts University, Chris Haviland and Matthew Turks at University of Illinois, Dave May at UC San Diego, who's the main developer of the Lithohistoric Dynamic Codes, PTOTN, and then a number of additional collaborators. So Menno, Sasha Brun, William Rezi, Boris Kaus, Max Rudolph, and a number of other folks. So first I want to start with an overview of the state of the geodynamics community, at least from my interpretation. So we now have a wide range of state-of-the-art softwares available for modeling geodynamic processes. This includes codes like Aspect, LMM, Pilot, Rayleigh, Sisal, SpecFem, and a huge range of other codes. These codes run efficiently on an HPC system. They're developed using modern software best practices. They're community-driven development efforts. But the challenge is, and what this talk is addressing, this state of the community is not the case for software that aids in the design, so the inputs, or the analysis outputs of geodynamic models. And for this type of software, we're for lack of a better term, we're going to call it geodynamic supporting software. So here are 2 examples of geodynamic supporting software from projects I've worked on. So this is from the work Daniel just presented a little bit earlier. So with geodynamic supporting software, one workflow might be is you might first start by extracting information from geophysical data sets. So in this case, this is software Daniel wrote to basically take this Lab2 data set, use PyGMT to extract profiles along it, and then using the depth of the slab information along these profiles, then port that information to the geodynamic WorldBuilder and create this initial basically slab and overriding plate structure for use in Aspect. Then after we run the simulation, then you might look at the depths of slab and dehydration. But then this step right here, when you're analyzing the geodynamic simulation, this was another set of software written in Python to do these calculations. Another example would be, so then this is work that was done by a PhD student, Sophie Pon, who worked with me a few years ago, where we ran long-term geodynamic models of continental extension, and we wanted to quantify how these fault networks evolve through time. So we used basically image processing software in Python to extract that information. This is in 2D in a given horizontal plane, and to basically then get all the way to the point where we have this active deformation field. So this is the inputs, and then we eventually extract where the faults are located. And very similar software has been developed by Tila Rona, Sasha Brun, Derek Newharth, Anglerworm, and others. This is in their Fatbox repository. And you saw some of the results, saw some of that software being used, I believe, in Derek's talk yesterday. So what are the challenges with this type of software? So a loose community exists through informal sharing for this type of software, but there's not a centralized and well-organized development effort. You might find the software located on Zenodo or maybe supplemental material repositories after the work has been published, but it's not necessarily discoverable without prior knowledge. This type of software obviously commonly doesn't follow software best practices, or it might only follow some elements of software development best practices. This includes things like version control, automated testing, dependency managing, peer review, et cetera. And it's often difficult to extend and reuse with similar geodynamic software. So for example, the software I've written, it may work with the aspect outputs, but it may not work for outputs with something like Pitot-10, 3D, LMM, or Underworld, for example. And it's also often not written using modern optimization techniques. So the solution we've proposed at NSF from this is to basically take all of this existing software and develop a centralized repository and community surrounding it. We're calling this effort GDMATE. This stands for Geodynamic Modeling Analysis for Toolkit and Education. The components of GDMATE could be software for pre-processing data. So this is basically analysis of geologic and geophysical data, generation of modeling inputs, for example, writing WorldBuilder files, post-processing of modeling data, and then also education. So this would be implementation of geodynamic modeling tutorials and teaching resources. And in addition to actually creating the repository, then we're also proposing to develop a user community through training activities and hackathons. So what would the benefits of GDMATE be? It would be discoverable, so it would be easy to find basically existing code that people have written and contribute to the repository rather than searching as a node or supplemental materials. It would be portable, so you could use it on different operating systems and different computer architecture, so either your laptop all the way up to like an NSF-style supercomputer. It would be extensible. So one of the key components of it is the design we have in mind is that people can easily add to it. So it's not a static repository, but it's basically any idea for something any software you write, which falls in the category of this supporting software. The repository design would be that you can easily add it in to our framework. It would be optimized. So we write things in a way where you automatically take advantage of Python optimizations, things like CIthon, Numba, or parallelization, and it would be intuitive to use. So some of the initial features we proposed, adding to this includes things like visualization tools we've worked on. This would be either using codes like YT, which is something Chris Haviland and Matt Turk have used, PyVista, PyGMT, fault extraction analysis tools, support for writing geodynamic WorldBuilder files, petrologic analysis, and then rheology toolkits. And there are a bunch of additional features, but this is basically a collection of everything we had the people involved in the proposal have, and then it would be expanded later on if this work is funded. How does this integrate with CIG? So then this is what we outlined in the proposal in the previous part of the talk. So then you could have a researcher, you have data, you know, process the data, run a simulation, analyze the results, and visualize them. This would be integrated heavily in Jupyter Notebooks, is one of the other features we've proposed. But then in CIG, as we're going to hear from Mo in the next talks, there's ongoing efforts at CIG to create educational tools based on Aspect and other CIG-supported codes. And then the hope would be is that basically tools we develop in GDMATE, these would be used directly in these CIG educational efforts. So as sort of a summary, this is the proposed work in review, which we hope to hear good news about later in the spring. Is this work for geodynamic supporting software? We would be integrating existing tools into a common framework following CIG best practices. It would be interoperable with outputs from different geodynamic codes, so it's not just restricted to Aspect. For example, in what we're proposing initially, you could use it with LMM, Pitot-10 3D, Underworld, and any other code that's interested in participating. It would be optimized to take advantage of modern Python techniques and parallelizations. We'll be hosting a number of community workshops and hackathons to hopefully build a community similar to the one we have for Aspect. And then after this 2-year period for the proposed work, then we'd hopefully have rapid adoption and continued funding and contributions from the community. If you're interested in taking a look, we have an initial repository for GDMATE. This work was funded by CIG over the last 2 years, and the development efforts were led by Dylan Dassey, who's now at Tufts University. But the questions I would pose to everyone here for the discussion section after Mo's talk would be, is this useful? So would having a wide range of geodynamic supporting software in a common actively developed repository be useful? Or is the current state of things okay for every, is it working sufficiently well? Another question would be have you developed geodynamic supporting software that may be of use to others in the community? And would you be willing to contribute it to a common repository? And then also, if you think this is a good idea, what functionality would you like to see in this type of repository that was not described in this talk? And that's all I had. I'm looking forward to your comments later in the discussion.
Thank you, John. And thank you for making the effort of proposing this and writing this proposal. I cross my fingers that it gets funded.
Us too. Yeah, we're cautiously optimistic right now.
Okay, good. We're a bit ahead of schedule, but that leaves more time for questions later. That's good. So Mo, if you want to get started.
All right, do you hear me? Do you see my screen?
I can hear you. I can see your screen, but it's not. Yes, exactly.
Yeah.
Yep.
No, it's fine.
Looks good.
All right. Well, thanks, John, for the introduction. As you mentioned, some of the work that we've been doing, and yeah, basically what I'll be talking about here is some of the work that we started at CIG last year, and that will be continuing for the next few years. And it's basically focusing on developing educational tool to enable students to have more access to computational tools and to allow basically instructors as well to have access to computational geodynamics tools that they can implement in their teaching and in their curriculum. So this is something that I've been doing with Lorraine, and like I said, started last year and I'll be continuing over the next few years. So there's just like some quick introduction actually to what's been done at CIG, which is basically an NSF cyber infrastructure that has for mission to enhance competencies within the geoscience community. And this is basically done by providing structure for developing geodynamic modeling software like Aspect, which actually like have been talked about like over yesterday and today. But also developing, hosting, and disseminating computational workflow to improve the capabilities of the scientific community and try to reduce some of the barriers in terms of reproduction and extension of research. The last point that I'm putting here on slide is what matters for this talk here is one of the other cornerstones of CIG is to promote widespread access to educational material for computational geodynamics. And that basically the aim is to nurture computationally skilled workforce and try to increase the discovery of the discipline through computational methods. So obviously those three objectives are interlinked and they feed into each other, but I'll be talking mostly on the educational component here. So the aim of this work is basically to develop modular teaching resources targeting upper division and graduate level geodynamic courses. And this is done by the integration of computational methods and tools in Jupyter Notebook environment to teach geodynamics concepts. These resources should enable and promote the training of students and increase, as I mentioned before, the discovery of the discipline. And it's one way actually of increasing and attracting more students into earth sciences. So as most of you know, and as you've been showing actually over like with the various interesting talks that you've presented, is that geodynamics is basically a field of earth sciences that relies heavily on computational methods to advance our understanding of earth systems. So the integration of field geophysical observation with numerical modeling is something that in the last decade have become actually an essential approach in geodynamics research. So this is why the need to incorporate computational skills into undergraduate and graduate curricula is something that's really much needed. So there has been individual effort I mean, there is already individual effort that exists, and many lecturers use computational methods and tools in their research lecturers that use computational tools and methods in their research, they tend to integrate those tools to some degree in their syllabus. But there are a lot of barriers into making this a widespread practice. And one of the main barriers that we face usually when we try to implement computational method in teaching is sometimes the lack of appropriate expertise of the instructor, the workload, because integrating those tools into the curriculum require a lot of work on the instructor side. And also like the software installation, because like if we want to make those tools available to the student, to a big class of student, then you need actually like to find a way to install those softwares on the machines that students actually work on. So this is why the effort that have been carried out within CIG to develop teaching material, which are openly available and easily deployable, should basically like remove some of those barriers and help instructors fill in the gap between what they have already actually in their curriculum and skills needed to leverage the potential of computational tools, and specifically here the tools that are developed within CIG. So our approach, and this is what we've been doing over the last year, was basically like to rely on feedback and the input from an education working group that was made and that was actually like put in place, and it involves several people actually that are involved both in research, in geodynamics research, but also in teaching. And you can see actually that you probably recognize most of the names that I have listed here. And one of the first things that we did is try to evaluate what's currently done in terms of geodynamics teaching. What are the new approaches that we should actually like investigate, and what are the core skills that students actually should acquire by this integration of geodynamic tools in the curriculum. So then once this first phase was done, we identified a roadmap actually that would allow us to develop and implement those resources and make them available to the community. So one of the key elements that we looked at the beginning was actually like, what are the different components that we have actually when we teach geodynamics, and this basically can be split into two components. So you have the geology teaching or geoscience teaching, and then geophysics teaching. Those are like two different components, and usually classes actually like that were actually like where geophysics is a heavy component actually like do actually like differ from classes where actually like geology is the main component. In terms of computational skills, there are like two components as well. So we have CIG software, so including aspects. And there are also other skills, actually computational skills that are very useful, which are like programming skills as well. So that are separate from the geodynamic modeling skills. So if we integrate those four different components, we manage to identify actually different fields and ways to integrate those four components when trying to build those educational resources. And what we identified is that we can actually see different learning paths. So like we have the geology learning path and the geophysics learning path, and each actually come with their like learning outcomes and objectives. And also like we identified, we decide actually that those resources, educational resources, should have different levels of complexity. So like we'll have resources that are like foundation level, so like those are like introduction to programming and geodynamic modeling, but also we'll have intermediate level and advanced level. And basically the advanced level will be the other end member where actually like the student actually like does a proper research project actually using programming and the geodynamic modeling software. In terms of development, we also identified like the key topics that we think are essential in terms of teaching geodynamics, and those are listed here, like heat flow, the usual suspect, heat flow, mental dynamics, elasticity, flexure, rheology, phase transition, melt, and then you have the last two components, the last two elements, extension and shortening, which are basically will be combining all those individual topics actually into making like a more extensive resource or like resource for like specific case-based studies. So as I mentioned at the beginning, so like the idea is to build those resources within a Jupyter environment, and basically the template that we came up with actually like include like three main components. So we have the domain knowledge component. So that's basically like a summary lecture where we introduce the geodynamic topic or concepts with the governing physical equations that will be examined. Then we'll have an analytical section. So that's basically like the implementation of the governing equation in an analytical way. And this analytical section will allow students actually to acquire some Pythonic skills and build core skills and modeling intuition. The third section within this like educational Jupyter Notebooks will be the geodynamic section, and this section will be dedicated to the use of CIG software like Aspect, and the aim of it is basically like to allow students to acquire some computational modeling skills. In terms of strategy in developing these tools, we have three main phases. We have the drafting phases, which actually will basically compile a draft of the Jupyter Notebook that will be shared with the education working group for their feedback. Once we have the feedback from the education working group, then we'll finalize the Jupyter Notebook that will be once again shared with the education working group for testing. And once it is tested, it will be released, and it will be released actually and put on the Geodynamics on the CIG website, which is the geodynamics.org. And I'll show you actually like something later actually like on the website, but like just to conclude on these resources. So like one of the key things that really important for us is to try to identify what's already existing out there actually. Like, so like there are a lot of tutorials, a lot of manuals and cookbooks that are out there actually that can be used and implemented in those Jupyter Notebooks. So this is actually like cool for you and for the community actually. If you have any material that you use in teaching and you think actually will be useful to be implemented in this effort that we're doing here, please reach out to me or Lorraine, and we'll be happy actually like to use some of the stuff that you've already using. So what I showed here is one approach to actually to tackle this aspects of educational resources, but we know that there are different approaches, and we are open actually like to in layer phases of this work to try actually and test other approaches to this effort. And obviously like I mentioned in first slides, like the one of the main ideas behind this work is basically like to support open science by and also like be more inclusive actually in computational geodynamics, in sense that allow students actually and lecturers to have access to those resources and allow them to implement those tools actually in their teaching and improve actually like the learning outcomes from their teaching. So I think I still have some time. Do I have like 2 minutes?
Sure.
Yeah, so what I'm going to show you here is basically a tool that was developed by René that we have now actually like on the CIG website. So if you go to the CIG website and you go to software, launch, and you go to aspects, and this is the tool actually that was put together by René, and it's been actually like on the website for a couple of months now. and it's basically an Aspect Jupyter Notebook. So this is Jupyter Notebook that has actually Aspect installed, and you can run Aspect from within Jupyter Notebook. And you can run it basically on the cloud through the HubZero platform, which is at the back end of the website. So if you launch the tool, so in here actually, like what you will see is a tutorial that I ran last October for a group of PhD students back in Morocco. And I run the entire tutorial actually on this platform. So it works actually pretty well. And basically, I just want to show you an example actually like that it works. So if I go to Aspect Basic, for example, and I launch this one. Yeah. So basically this is here actually I run an example of the 2D convection model. Yeah, for some reason actually removed some stuff that I did earlier. But anyway, so like you can run aspects from Jupyter Notebook. That's basically what I wanted to show. And yeah, so like I said, so this is a great tool, and this is like one of the great things actually that we'll be using for those educational resources, because like those topics that I mentioned and the resources that we'll be building, at least like the for now will be based on will be using Aspect. So having this tool at hand it's really useful. And like I mentioned, so this is a workshop that I run over 3 days, and we use actually Aspect to run different models, simple models, and it works pretty well. So like, and you can use it also like to visualize the output from the models that you run here. So yeah, so if you want actually, and I believe that we can request actually like, because like like if you run something actually like for like a big class or a big group of participants, then actually like we can, from CIG side, we can request actually more computational resources to allow you actually like to run several models simultaneously through the platform. But for that, you need actually like to ask for additional resources through CIG. Yeah, so that's what I want to talk about. Thank you.
Thank you, Mo. That sounds like a wonderful resource. All right, let's open the floor for questions. Were all the questions from the previous talk answered in the chat? Renee, go ahead.
Yeah, thanks both. John, I have a question about the status of GDMATE, and in particular, we've talked about this a while ago, but have you made a decision on the types of programming languages or data formats that you want to include? Is it essentially open to anything people might have, or are you imagining a certain language or format that's going to be used?
Right now, we're going to be sticking with Python, and that's what we proposed as the initial development. We thought very hard about, at the beginning of this is 2 years ago, about just focusing on Julia. Julia has a number of advantages, namely the optimization. So there's one, or because it's just in time compiled, you don't have to do that with Numba in Python, because the just-in-time compilation of Python, it only works with some packages. And also there's like multiple ways to do parallelization of Python. So it actually becomes a bit of a challenge to figure out what's the best method to use in a repository like this. But for now, we stuck with Python because some of the packages in Julia, they're not mature enough to be used yet. So like image processing, we looked carefully at some of these, and some of them are very much in a development phase. So my suspicion is, I talked extensively with Boris Kaus about this, and Boris has moved on to Julia, And what he does is from Julia, if he needs a Python, if he needs a feature that's not implemented in Julia, he calls Python from Julia. And there's things I don't, you know, that's adds a whole nother element of complexity, because what we want this repository to be is something people can easily contribute to. And that's not easy, but my suspicion, which may or may not be correct, is that over the next 5 to 10 years, the community will transition to Julia, just because working in Python for all these different reasons, for the optimization reasons, it's really hard to optimize things in Python, unless there's some major transition of Python where the community center serve rallies around 1 or 2 optimization methods. Who knows? But for now, it'll be in Python. But we're actually writing. We're proposing to write the repository rather than an object-oriented style. We're going to write it in a functional style. Oh, because then if we do decide to transition to Julia, that would make that transition a little bit easier. In terms of inputs, the idea is any input people want: HDFI, VTK, ASCII. That is not so much of a barrier. We want to create, we're going to have a data IO section, which it would kind of be subdivided either based on data type or code, or some mix of the two. And in the end, it's pretty easy to get data into Python as it is now. That's actually not that much of a challenge. It's really the optimization is really the hard part for very large models. But the idea is to make it open to anyone who's interested in participating.
Okay, cool. Thank you.
Yep.
Daniel?
Yeah, super interesting. And I had a question for Mo. Just because I tend to use Jupyter Notebooks a lot because I like how it's more intuitive and easy to visualize the code and stuff. And so I was just wondering, as someone who's not, in a teaching position for other grad students here, is there anything that we can do to help or contribute to this initiative?
Yeah, I mean, like I said, if you've been using actually some piece of Python scripts actually in either in your research or in teaching that you think actually might be useful, then that's something that actually we would actually to have access to actually, and see actually if it's something that we can implement in some of the notebooks that we're building. So but yeah, also when it comes to testing those notebooks, once actually we build them, actually that would be actually something that I think will be of interest actually to us, is people from the community that can test them and provide their feedback actually, how they can be improved, or if there is things actually that could be changed in a way to make them actually more useful for the community. So there are different ways in which I think the contribution of the people from the community like you actually could be very useful.
Okay, cool. Yeah, I'll definitely just, through working with you guys, I'm sure I'll find ways to help out, and I'm super interested in helping out, so.
Awesome.
Do you have any other questions? Mo?
Okay, can we ask questions for the other talks that
Of
we
course,
had, or...
yes. Yeah.
Yeah. I don't know if Antoinette actually is still here, but I have a question about the something that you mentioned. Yeah, hi. So something that you mentioned so you said that in your model with the flat slab, you see actually that you have subsidence actually in the overriding plate. And I was wondering if based from your model, if you can say what's driving that subsidence, what's the process actually that causes that subsidence in the experiments, because you mentioned that it's something that's seen actually in from the observations from natural systems. So I was curious actually to know if from your model you can say what's the driving process.
That is an excellent question, and I normally like put that in and leave that there and hope that people will ask me a question. No one has ever asked me this question before now, so thank you for finally making my hopes and dreams come true. So that is really interesting, because if you look at the horizontal shear stress, you can see that there is extension in the first bit, right, like towards the margin where there is the primary substance, and then there is compression, and you can actually see that the topography increases over there. So you've got like a minor, where you've got like some compression over there, and that's where you see like the secondary sort of, the divide between the first piece and then the second sort of and a second sort of source of subsidence within the continental interior. And then you see the horizontal shear stress go from compression to extension again, where you've got the secondary subsidence. And again, if you look at the pressure, that corresponds to an increase in negative pressure. So wherever you've got like this slab suction, it seems that corresponds to you're pulling down, then obviously you're pulling down the surface. So essentially, like the slab, if this is the slab and this is the overriding plate, you're kind of squishing them like that. So that is what's causing the secondary subsidence. The first one is where you've got like the first mini wedge or the first dilation zone, and the second one is where you've got the second slightly larger wedge. And the second subsidence is less pronounced than the first one, because you've got less of a negative pressure in the second part of the wedge, right, in the second dilation zone, if that makes sense. Yeah.
Okay, so yeah, thanks a lot for the answer, but it was wondering it's not tectonically driven.
Well, yes, it is, right, because it's the fact that you've got the slab, right? Like it's the slab that's going up that's causing this negative pressure. I don't think I maybe understand your question. What do you mean by not tectonic?
Yeah, no, I mean, okay, no, yeah, it okay, in that sense it is, but I was wondering actually if there is like if it's driven, if it's okay, so it's driven by the is it gravity driven or like stress driven? That's what I meant.
Stress driven.
Stress driven. Okay, thank you.
No worries.
Julian?
Yeah, I had another question for John, and maybe you said that and I just didn't so I was wondering for the GDMATE, what kind of, so right, you said you want to be able to read in different codes. Have you thought about sort of what output format? Like, did you just want to read the VTU or a different output format? Or I was just wondering, because lots of codes probably already produce output for ParaView, so that would be easy. Because I thought for most users, it would probably already just be useful to have a general script that reads in the output and then be able to do whatever they want in Python.
Yeah, no, absolutely. And so then again, like the hope is to support a number of different formats. And so right now there's actually the Python scripts are written. There's a couple of different ways to get data into Python. For anyone interested, send me post a question to Aspect user forum, and I can post some example code about how to read it. But it turns out there's a couple of different ways to get in. So for example, there's a visualization package called PyVista, which is for visualizing finite element models. That actually has a bunch of built-in readers, which easily read in all of that data. But for a code like YT, which is based on unstructured meshes, not messes, they have their own class of readers, which they write for these different data formats, because their code is highly parallelized. But I guess the hope is to read in any reasonable format, be it HDF5, VTU, VTK, NetCDF, ASCII. The hope is that we can build a reader class which easily allows implementing all these things. And that's actually a large chunk of the work that we proposed in there. We know, it's a lot of work to get all these things optimized. So that's actually a non-trivial amount of the effort in the first 2 years is building these data IO classes, which make it easy to get things in there.
Yep, that makes sense. Thank you.
Oh, of course.
Mo, you mentioned that if we would want to teach a class and use the available Jupyter notebooks, that we could request like computing access from CIG. Is that like
Yeah.
How scalable is that? Like what uses do you see in the future?
I don't know. I mean, like it's how scalable. I don't know. We should. I mean, Lorraine might actually be able to answer this, but like just for an example, the workshop that I mentioned that I run in October. So there were like 10 participants, and we had access, I think, to 8 cores. Was it 8 cores? I think that we got access. I think usually there are like just 4 cores actually on the HabZero platform, but I think we had more than 8, but like we had access to more cores actually, which allowed us to run several models actually at the same time. So each of the participants was able to run their models actually on simultaneously. But like, yeah, I think there is, Lorraine might actually be able to better answer your question.
So I ask Renee this every single time. There's a certain number of cores available to people who spin up that we have dedicated access to. And I'm going to say it's somewhere 2 cores shy of 16. Beyond that, it's theoretically infinitely scalable because we would contact HabZero and they would contact their provider to configure the resources that are needed. That said, it's probably once you ask for more cores per seat, then there is an expense involved. And I'm not sure that they have really figured out what that cost structure is, but it is available and we can look at that. Most of our, I think, tutorials run on a couple of cores. There are larger examples. I know that people would want like access to 4 cores per, seat. So we hope to be able to meet, a reasonable demand for that.
Okay.
As well as for instructional support for classes as well.
Because I think actually like we have now actually like by default, it's like 4 cores by seed. So like if you open a session and you want to run actually like you can run actually like a simulation on 4 cores. So because that's what I've tried actually like.
Do 10 people then also have access to 4 cores, or are they sharing those 16?
I think
sharing.
Yeah, I think it's shared. Yeah, I think it's shared. That's why actually you need to request actually more if you need actually more.
And is there an official procedure to request more? Do we just send an email, or like what do we do?
Submit a ticket.
Open the ticket.
Yeah, let us know, seats, core hours required, and, for what duration. Because sometimes we realize people also might want some access post a training session for people who still might want to run some toy models. So what wasn't shown also is there's an aspect terminal as well. So you can run this from the command line by setting the appropriate environmental variables. Within the notebook, you don't need to set those, but if you're working in a terminal shell, you do.
You don't actually. They should be set in both tools. So you have the option either to run in the Jupyter Notebook or to run in a environment that looks more like a very simple desktop environment.
No, I tested. Timo is right though, because within the Jupyter Notebook, if you opened a terminal, you need to set the environmental variables. But if you ran it in the notebook, you didn't. So that was that hang up in that issue. So.
Okay, interesting. I've never tried to create terminal in the Jupyter Notebook tool, but there's a separate tool that is completely without a Jupyter Notebook. And that should have all the necessary environment set.
Okay. Yeah, I didn't either. So until he mentioned it.
All All right, John, you have a question?
Yeah, or sort of two comments. For anyone, as this matures tool, as this tool is maturing, if it's not the right tool to use for your teaching, and you want to use Aspect in teaching now, I strongly recommend using Docker for that. So we ran a large tutorial for Cider, at Cider for an Aspect tutorial and used Docker. And I don't know, there are probably 50 participants there or something like that in the room. And 45 out of 50 have worked on their computers or a range of platform. And it was a lot easier to use than VirtualBox. So long term, this is going to be an amazing tool for teaching. But in the short term, if you're looking for a tool to use, using the Docker container works. It worked really well in a large setting. So that would be my recommendation. And my other recommendation is, so this is a half question, half comment for Lorraine and Renee, is that, so Hub Zero uses the CST, UC San Diego supercomputing resource of understanding. And what I've done in the past, and I think, Lorraine, this was for when we did the s'mores program, is we submitted an educational proposal to exceed, or which is now access to get time for computing in the classroom. And so it may be possible to get a much larger amount of resources through Hub Zero through one of those grants. I don't know if it's possible to link a grant to the Hub Zero resources, but that may be one option for people in the US. There's at least a pathway through access to get time for educational computing things rather than just research things.
Yeah, that is theoretically possible, actually, that it's either through the Aspect container or through the Jupyter Notebook container to access outside resources. Nobody's tried that yet. So if you're sort of interested in doing that, let us know, because we'd be interested in sort of pushing that forward as a sort of, as a beta model.
All right, I no longer see any raised hands, and we've moved into the time schedule for a break. So I would just like to thank all the speakers and all the people that were involved in the discussion. Thank you very much, and everybody watching, obviously. Renee, I don't know if you have any final words, because we will have another session after the break, right?
That's correct. We will have another session after the break, but that is again one of these optional sessions that is mostly there if you want to discuss something, some problem or some possibility, some feature of Aspect, or also if you want to just have a private meeting with any other participant here in the Zoom call. That's also a time to set that up. We can set up breakout rooms if you want to. But the official part of the program, so the scientific presentations, is more or less over here. And I want to thank again all of the JS, all of the speakers, all of the participants for making this a great meeting. And maybe see you at the top of the hour, or maybe at one of the bi-weekly user meetings in the future. Thanks all.
Thanks, everyone.
Thank you, Renee.